open the school which is devoted to the modern problems of stochastic processes. And the schools continue, I hope, tradition, which arise from cooperation between our Institute of Mathematics of Ukrainian Academy of Science, namely of our Department of Random Processes, and Jilin University. Today, school is devoted to different aspects of the modern stochastic process theory. Why I say different? Because when we study some branch of mathematics, nevertheless, stochastic processes or abstract algebra or whatever you want, we always have different reasons to do this. One reason lies in applications. We want to get the description of the events in physics, biology, chemistry, and other natural sciences using the tool from our branch of mathematics. In our case, from stochastic processes. From this point of view, you will face the lectures of Katerina Kustareva devoted to machine learning, and it occurs that despite of the idea that this subject arise from purely applied math, from statistics, from statistical analysis of very simple from the first look of view subjects, it occurs that nowadays it becomes to be a very deeply developed branch of stochastic process theory involving such notions like infinitely dimensional spaces, correlations functions in multidimensional spaces, and so on. Another one is the idea to create models for, again, for some events or some objects in natural science. Today we will start my lectures devoted to attempts to model linear polymer molecular. We will see different aspects of this theory too. Another lectures of Katerina Glinina will be devoted to point processes which arise in stochastic flows. And again, this is not an abstract subject which we study only due to our interest to develop some new machinery or some new mathematics. Of course, it can be, but since people began to study turbulence, maybe it was already 2 centuries ago. The idea that in turbulent flow we have small vortices which interact one with other and have complicated behavior together is present in the science, and this problem of this description of such behavior deserve several approaches. One of them is related to stochastic flows, and Katerina will show us how it looks like. And the last speaker will be Georgy Ryabov, who will present you very abstract from the first point of view, subject related to theory of Gaussian measures in abstract spaces, and you will see from the first look of view, again, you will see very abstract statements related to infinite dimensional space, properties of measures on infinite dimensional space, but they also are related, for example, to my lectures devoted to modeling of linear polymers. And so one can conclude that all these lectures contains material which can be useful in applications from one point of view, and from other point of view has its own interest because it is a part of the modern theory of random process, as I said. Ending this short introduction, I wish success to all participants of the school. And I have small announcement that we will try to produce the notice of these lectures. The notice will contain more material than will be presented on the lectures, and also contains a list of references and so on. Please don't hesitate to ask questions during the lectures. Moreover, if you will have some questions and after the lectures, then you can send email to organizer Katerina Glinina or directly lecturers in order to clear some moments which you want to study. Since then, let me introduce myself as the first speaker today, and my lecture will be devoted to the beginning of the study mathematical models of linear polymers. Let's start, and I will demonstrate my screen. Hope it is visible now.
Yes, we can see.
Okay. And now let me. Okay. My first lecture will have introductory style, and is devoted to properties of linear polymers. What is a linear polymer? Linear polymers are long molecules consisting of chained monomers of one type or few types. Usually, monomers in this chain are bivalent. So you see that every monomer can be connected with its neighbors, especially with two neighbors. So we get a long chain. This long chain usually consists of a very large number of monomers. It can be even 10 in power 4 or 10 in power 5. Such monomers arise in biology naturally, as for example DNA, proteins, and from other side, maybe already 70 years, arise artificially because people want to produce linear monomers solute. Why? it occurs that chemical properties of linear monomers are very different than properties of usual liquids, gas, and so on. Maybe from the general course of physics, you remember that there are three phases for regular chemical or organic molecules. It can be solid, it can be fluid, and it can be gas. But maybe even 1.5 centuries ago, people discovered that there are some very strange solute of something. It was unknown at that time. That have very strange properties. For example, if we have semi-permeable membrane, it occurs that this solute cannot pass through despite of the looks like liquid. After maybe 30 years of investigations in 30s of previous century, it was discovered that this solute consists of long molecules, and these long molecules are not like lines. They can change the shape. Why it is so? Because chemical bonds between neighbors monomers in non-polymer molecule are flexible. Here I draw a picture which is, by the way, not far from reality. Why? You know that every physical system wants to get the stage with minimal energy. It occurs that when we consider a pair of monomers which are related one to another by valent bond, that there are several, usually three positions in space, oriented in space, where this connection gets minimal energy. So you can imagine that in this long polymer chain, long monomer chain, every bond triggers instantly. So the chain can change its shape, and you can see different solute of linear polymers. One contains more or less linear lines in some fluid. Another one contains lines which are slightly knotted, and the last one contains so-called polymer collapse. And these three pictures reflects the idea that differently from usual water, for example, or metal, polymer solute can have 5-phase state, not 3, but 5. You see here is the one state which was like a fluid for usual chemical molecules, But for polymer, we have different properties related to the shape of this of the polymer. So the value physical features of linear polymer are the following. We want to understand how this chain is organized in the space. One can try to do this just calculating or just measuring the end-to-end distance between the ends of the polymer. Of course, it can happen that it is a very long loop with small end-to-end distance, but let me say you that all characteristics of polymer which we are discussing in this lecture are statistical. So when we say, okay, under this temperature condition, polymer has end-to-end distance like some L. It does not mean that every of them have it, but statistically it means that in mean, for example, it is equal to L, and it means also that more or less our chain is grouped in such a way that this is really diameter of the chain as a as we have a habit to define diameter for any for any subset of the Euclid space. The same characteristic which also characterize the shape of the polymer is a radius of gyration. This is a radius of small ball which contains the polymer knot. Of course, it is related to end-to-end distance, and even sometimes, especially in physical works, people say that L is just 2 multiplied by R. Yeah. But what is interesting? That to this characteristic do not pay attention to any shape of the polymer. But it occurs, and it was discovered recently, maybe in 2006. It was even a Nobel Prize given for this, that geometrical shape of DNA knot has influence on gene expression. So we don't need only to only understand chemical properties of the polymer solute related to its sizes of the polymer knots, but it will be very good to model and to understand the geometrical shape of the polymer knot. And what is interesting, everybody of you knows that DNA has a double spiral structure. So it looks like this. And due to the, and actually this double spiral structure is the protection of alive creatures at our Earth from the influence of small cosmic particles which came instantly through us and break some lines in DNA, but due to complementary acids in its structure, these lines can be recovered. And moreover, due to this complementary structure, to double spiral structure, DNA can cross itself exactly as it shown in my picture. This means that DNA node can change its topological type, and it do it instantly. So we have such property, and also what is interesting that we have the so-called DNA folding. Maybe everybody of you have seen a picture, have seen a picture of DNA in different physical books, and remember that it is like very dense knot. It is tightly packed due to the van der Waals force. Even people in physics say that it is polymer collapse. So you see very different features of long polymer, long linear polymers. And now let us begin to think how we can model. Relatively to things which I mentioned, one can try firstly to get the model where we can calculate, estimate end-to-end distance or radius of gyration. As we said, the shape of polymer change randomly. So maybe it is a good idea to try to model our polymer by trajectory of some random process. Let us try to do this, and we will. Now let's get idea what we have to do. To get this idea, we consider the new for us, but rather old characteristic of the linear polymer. It is called by Flory index. Denoted by N capital the number of monomers in the polymer molecule. Then it occurs that end-to-end distance or gyration radius of linear polymer looks like a constant multiplier of n in some power alpha. It is not linear with respect to n. We can expect that it can be linear only in case when our long molecule looks like line. So on practice, one can see that we have such relation for radius of gyration, and this alpha is called Flory index. It can be estimated using some energy calculations for linear polymer. And it occurs that alpha can be like 0.4, 0.7, and so on. But it definitely is less than 1. So if we model a linear polymer by the random curve in the plane or space, it must have Flory index less than 1. Fortunately, we have very simple but very powerful and very interesting mathematical object which satisfies this requirement. The most known and simplest one is a trajectory of a simple random walk. Here I consider plane case. By the way, it is not artificial because there are at least in chemistry, there are a lot of cases where we need plain solute of plain polymer solute and continue polymerization after this solute became to be hard or elastic. So let us consider planar case and consider ID random vectors on the plane, which are very simple. We just go parallel to coordinate axis with equal probabilities in both directions. Now define xn as a sum from k equal 1 to n of epsilon k. Then we get trajectory of our random walk, and one can consider this trajectory as a model for linear polymer. But what a problem we face under this consideration. Under this consideration, we get the following good from first point of view, good from the first point of view news. So everybody know central limit theorem. Now xn is just a sum of independent equidistributed random vectors which are centered. So one divided by square root of n xn tends in distribution to normally distributed random vector with parameters 0 and 1/2 of identity as a covariance matrix. From this point of view, the expectation of xn has speed of growth like c multiplied square root of n, so Flory index is 0.5. It's very good. We get what we wanted, maybe, but there is some problem. The problem is the following. Physical linear polymers satisfy so-called excluded volume rule. It is very simple. We cannot put two monomers in our linear chain in the same place into space. But for a random walk on plane, we definitely have points of self-intersection. It can be even proved more that we will have such points with probability 1 if we have put n tending to infinity. Yeah? So for sufficiently large n, we maybe have a lot of points of self-intersection. The question arises how to produce more realistic models of linear polymers using this random walk trajectory. There are several ways to do this. One way is to consider conditional distribution of a random walk under the conditions that it has no self-intersection. Because for fixed n, you can imagine that there are some trajectories which has no self-intersection, and we just can consider conditional distribution of our trajectory of random walk for n steps to this event. It can be done, it is hard for calculations, and in this way we obtain so-called loner self-avoided random walk. But the next idea is more physical, and it looks like this. Suppose that we will arise loops which we obtain when we have points of self-intersection. Exactly as I draw. When we have the loop, which is marked by red, we just erase this loop. In this way, we get, of course, the trajectory, which has no self-intersection, but what happened? It occurs that in mean the number of steps which remains in this trajectory and the initial n steps is approximately logarithm of n. So it is not a good idea to consider such trajectories. You remember Flory index is n in some power. Yeah. But still, loop-erasing random walk is an interesting mathematical subject, and you can find a lot of papers about this, even myself, devoted to different properties of loop-erasing random walk. The next way is based on the idea of Boltzmann. It came to the beginning of the previous century, and the idea is following. Maybe we can consider some energy related to trajectory of random walk. And this energy must be bigger for trajectories which have self-intersections. It is natural because when you want to put two monomers closer than they can be from chemical reasons, maybe you have to spend a lot of energy. So we just introduce the Hamiltonian for the trajectory of a random walk. In discrete time case, it is a very simple expression which looks like this. We just calculate the pairs I, which is less than j, for which xi is equal to xj. Yeah. And finally, consider the expectation. Consider for some alpha the expectation of exponent in the minus alpha lambda n. Then define new probability p with tilde, which has a density psi with respect to initial probability, this probability measure. And this density psi has the following form. We just have 1 over Zn multiply on the on this exponent. So we have C that when we introduce this probability measure P with tilde, depending of course of value of alpha, but we try to make probability of appearing of trajectory with a lot of self-intersection very small, because for such trajectory ln will be relatively big, The probability that such trajectory appears is small. The more energy we need to build some artificial object, then the probability that we will take randomly this object is less. This is idea which arises from Boltzmann. He insisted that this is a general principle of any physical systems. He did not investigate polymers separately, but it works also here. So now what we have to do? We have to understand the behavior of Ln. If we want to say something about Flory index, about the radius of gyration, and some other characteristics of the polymer model which we obtain, we have to understand the behavior of Ln. And it is well studied, and it is my pleasure to say to you that you can find a lot of materials about this in the book of Professor Xia Chen. Maybe some of you know him, and he is organizer of our school too, and well-known specialist in the world in this field. So you will find a lot of interesting facts about the self-intersection for random walk and Wiener processes in his book. But now let us get the feeling what we can obtain, for example, this lambda n. And to get this feeling, we don't need very hard calculations. We just can recall to ourselves that the random walk is the discrete model for Brownian motion. So under appropriate scaling, random walk approaches the Brownian motion. We can get understanding of behavior of Ln, consider the random walk with Gaussian steps. Namely, consider the instead of the sequence of epsilon k, consider now the sequence psi k of independent random vectors which has standard multidimensional Gaussian distribution. So it has zero mean and unit covariance matrix. Then define eta n as a sum from k equal 1 to n of psi k. We just substitute epsilon k by psi k. Then one can consider self-intersection. But now we face a problem. And problem is purely mathematical. That psi k has continuous distribution, absolutely continuous distribution. So the probability that eta n will be equal to eta k, for example, is equal to 0. Yeah? So what to do? And then we look for such interesting substitution of indicator. And this substitution is a delta function from the difference of our random vectors. It must be well defined, because right now we don't know what is the delta function from the random vector. In Gaussian case, when vector is Gaussian, and in some more general cases, it can be properly defined. I hope you will see this in the lectures of Georgy Ryabov. But now we don't need to proceed with all theory, just let us take the expectation formally. And it is very easy. What is the expectation of the function now? Delta function from the random vector. It is the integral from this function multiplied on the density of this vector. That's all. But when we consider integral of a delta function with some good test function, it is exactly the value of this test function at the point zero. From this point of view, when we take the expectation, we get nothing else than the density of the difference eta j minus eta I at the point zero. So one can now easily conclude that in the planar case, expectation of Ln with tilde is like n logarithm. It's pretty big. So one can conclude that we have a lot of self-intersection. As I said, one can continue studies in this direction, and it is there exists a well-developed theory of discrete linear polymer models modeling based on the simple random walk. As I said, when we make the notice of these lectures, you will get the references. There are a lot of books related to this subject. Now, let us think what will happen when we substitute the simple random walk by the random process with continuous time. And again, we take simple random walk as the most developed, most distributed model for discrete time process. Then the same is a Brownian motion for continuous time. But you remember that one of the important properties of Brownian motion is independence of its increments. And we have to obtain some motivation why we use the process independent increments. Actually, it arises in physics. As we said, one can change the angle between chemical bonds in linear polymer chain which connect neighbors. Due to this, when we consider parts of polymer which are placed on some distance along the chain, then the angles between these parts change independently. So from this point of view, one can think that maybe it is a good idea to consider the Brownian motion, trajectory of Brownian motion as a polymer chain, a model for polymer chain. It is true, at least from the point that this trajectory have a lot of good properties, and it's well investigated. But we face the same problem as we have for the planar simple random walk. Namely, it is known from the theorem of Dvoretzky, Erdős, and Kakutani in 1959 that a Brownian motion on the plane has the points of self-intersection of an arbitrary multiplicity. It is interesting. Arbitrary multiplicity, even count multiplicity. This is interesting theorem, and despite that its proof is rather technical, and the idea is just applying Hofbauer-Cantelli lemma to some special events that trajectory of planar Brownian motion will hit some set of small squares in a plane. It is very nice. It has very nice conclusion because you see we have as a conclusion that we even can have infinitely many infinite multiplicity of point of self-intersection. But it occurs that there are a lot of points of self-intersection. So again, as before, we have to calculate how many this point the trajectory has. So let Wt be a standard planar Brownian motion. Then analog of Ln, the number of self-intersection for simple random walk, in this case can be the expression of the following kind. This is the integral over delta 2, delta 0 of Wt2 minus Wt1 dt d1, dt1 dt2. Here delta 2 is a simplex, 0 is less than t1, less than t2, less than 1. Again, I use here expression for delta function from the random vector, but as I said, at least in Gaussian case, it can be defined very properly. And now everybody can easily calculate that is an expectation of this random variable in brackets is equal to infinity. Yeah, it is very easy to check. And what is the reason why it happened? The reason is that actually the Brownian trajectory is appropriate for as a fundamental tool for building of the polymer model only from the statistical point of view. Brownian motion has a very nice for mathematicians, but maybe not very good for applications property of self-similarity. What is self-similarity of Brownian motion? Suppose that we have a trajectory of Brownian motion. Take a point on this trajectory, take a small ball near this point and zoom it. And what we will see? Near this point, we have a lot of self-intersection. It happened, this intersection happened immediately after time t, if this red point is corresponding to time t, and immediately before time t. So, and then if we take another one red point here, again zoom it, we will have exactly the same picture. We will have again a lot of self-intersection inside of this ball. So we again have something like this. So now we understand that there are a lot of non-necessary from physical point of view self-intersection, but they are all calculated in this expression. So what we have to do with it? To avoid this large number of self-intersection which arise when T1 is very close to T2 in this expression, we need to do some renormalization. We need to subtract something from this delta zero in order to restrict such intersections which arise for very close values of the time argument. And it was done in very different, I must say, in very different way by a lot of people. Let us mention Klaus Semanjik, Evgeny Dinkin, J. Rosen. Klaus Semanjik did this from Euclidean quantum field theory necessities. Dinkin proposed a very interesting procedure. We will consider it later. Devoted not only double self-intersection but self-intersection of any multiplicity. J. Rosen discussed renormalization for self-intersection not only for linear process but for state processes and so on. What is the renormalization? Usually people subtract something from the value which is infinite. Term renormalization arose in physics in early 90s of the previous century and is related to ultraviolet divergences series in description of interaction between elementary particles. And it was proposed by several prominent physicists, Dirac, Dyson, then that we just subtract from one divergence series another one to get the right answer. Here we can do the same, but Semanjik proposed another procedure, and let me recall it to you. Here is it. So we consider our simplex delta 2, and now we just try to organize the following sum. Let us note that if we have such integral, double integral from a to b, c to d, delta wt2 minus wt1 dt1, then it is well defined. At least now everybody can take expectation and check that it is finite. Yeah, it's good. Because now we have this relationship between A, B, C, D. So then we can consider the sum of integrals over such squares as I draw in the picture. It occurs that this sum converges, yeah? And one can see that it is one of the ways to define renormalization for self-intersection local time for Brownian motion. As I said, there are a well-developed theory of polymer model based on this self-intersection local time as a Hamiltonian. But let me mention several questions which still are solved. The first one, theory is only statistical. What do I mean? Theory is only statistical. I mean that what about shape? About shape of the polymer. Polymer. Yes, we see that maybe we can estimate radius of gyration. It can be done. Tomorrow we will discuss some results related to large deviation for it. But we have not any idea about topological type of the obtained knot. And moreover, this self-intersection local time can be used as some geometrical characteristics of the Wiener trajectory. But the trajectory is non-smooth. What I mean? Maybe people who study already general theory of stochastic process know that Wiener process has no derivative at any point. It has non-smooth trajectory, highly non-smooth trajectory. They are only Herder order less than 1/2. From this point of view, it is slightly unnatural to consider such trajectory, such curve in the plane or in the space as a model for a polymer. We cannot discuss the shape of the obtained random knot. It has infinitely many self-intersections and so on. So at least from the first look of view, it is not applicable to consider the geometrical or topological notions for Wiener trajectory. So our aim for the next lectures is the following. We will try to overcome these problems. So finally, we will get smooth trajectory, which for which we can discuss topological type, which can move in the space and change its topological type. For today, that's all. Thank you for attention. Maybe somebody have questions or comments, please. Okay. If there are no questions, then now we have a break, 15 minutes up to the next lecture. Thank you for your attention.
Thank you. So let's have a break.
Mhm.